So basically, we're studying the details of what happens when you charge a capacitor using a resistor and a battery. So you have a battery right here, voltage of the battery. So details of what happens when you have a resistor and a capacitor. So let's say the capacitor is initially uncharged. So then the battery starts sending current that way and starts building up charge on the capacitor. So initially, the capacitor, if it's uncharged, there's nothing to impede the flow of that current, right? But then as it builds up charge, it kind of acts like a backward battery. So as the charge is building up, it's almost acting like this. You have a voltage of the battery, imagine a resistor, and then imagine a battery that's opposite, opposing the original battery, because you see the positive plate is here. So it acts as if it's a battery that's fighting against the current of this guy, you see. So we would expect, therefore, as the charge of this to build up, we expect the voltage of it to also build up. So I'm expecting the charge as a function of time to increase. I'm expecting, because C is equal to Q over V for the capacitor, therefore voltage is equal to Q over C, right? So as the charge is building up, I'm expecting the voltage to also build up, right? And then as it starts to build up, what's going to happen to the current? This, because it's behaving like an opposite battery to the original battery, I expect the current in the circuit to drop as a function of time. And then eventually, when it's fully charged, its voltage should reach the same as the voltage of the battery, right? Let's see here. Its voltage should reach the same as the voltage of the battery, right? Or at least asymptotically reach the voltage of the battery. And then the current should reach 0 at the end, once it's fully charged. And then the voltage of the capacitor should reach the voltage of the battery, you see. So that's kind of what we're solving for, is we're solving for what the charge, how the charge of this RC circuit, how the charge increases as a function of time, how the voltage of the capacitor increases as a function of time, how the current in the circuit decreases as a function of time, and then how the voltage of the resistor also decreases. You see, so since these are in series, if the voltage of this goes up, the voltage of that should go down, because the two voltages added up give you the voltage of the battery. So this goes up, this goes down. You see, so the current goes down, the voltage of the resistor goes down. So then we do the Kirchhoff's loophole this, we say, okay, we gain dB, then we lose IR going through the resistor. The amount of voltage that we lose is the current times the resistance. And then the voltage that we lose here is going to be Q over C, right? The voltage across the capacitor is the charge over the C, and then that's equal to 0. So we see here, current is the rate of flow of the charge, the rate of flow. So mathematically speaking, it's the derivative of Q. So we set up here, let's see, this goes over there, IR plus 1 over CQ. And then we can say R, and then I is equal to dQ dt. So basically you have here the resistance times the rate of change of, or I should say, instead of saying rate of change of the charge, I should say rate of flow of the charge. It's the rate of flow of the charge. So I is dQ dt, and then 1 over C, and then Q. So you have a differential equation here. you have something that looks like this. You have some constant. This is a constant, so let's say 6. And then this is also a constant, 2. And then this is y prime plus another constant, such as, let's say, 1/3. So I'm just saying, what if this was a regular differential equation that you solve in calculus class? You had a constant, you had some constant, you had y prime, and then you had 1/some constant, and then y. How would you solve a differential equation like that? So what function is there, y, such that when you take 1/3 of that function and you add 2 times the derivative of that function, you would get a constant. So what kind of differential equation is that? Have you guys done differential equations? So this kind of differential equation is a first order differential equation, right? First order differential equation, and it's pretty easy to solve because if you have a function as a function of t or x, and you want that function times a constant plus the derivative of the function to equal a constant, well, the only function is that there is whose derivative is proportional to itself is an exponential function. So the general form of this solution is y is equal to a e to the bx plus, let's say, d, right? And then you're going to have y prime is going to be the derivative of this. So then that's going to be a b e to the bx. Right, because the derivative of an exponential is just equal to itself, except that the coefficient comes down. And then you have here b a b e to the bx. So then we can substitute this into here, and then substitute this into here, and see what a and b and d have to equal. Okay, so then you're going to have here 6 is equal to 2ab e to the bx plus a/3 e to the bx plus d/3. So then if this has to equal to this for all values of x, you see, for all values of x, this number has to equal this. So then what should happen? If I factor out the e to the bx, 2ab plus a/3 plus d/3. So in other words, in order for this equation to satisfy that particular differential equation, this number in front of the e to the bx should be 0, right? This thing should be 0, so that this side should equal that. So the 2ab plus a/3 should equal to 0. And then what do we conclude from there? A and a cancel. And then 2b equals negative 1/3, right? And then b is equal to negative 1/6. So b, the power of the exponential function, has to be this, so that this exponential function can satisfy that. And then what should d/3 be? d/3 should be equal to 6, right? So d/3 should be equal to 6, and therefore d should equal 18. So we're learning how to do a general differential equation, then we'll take the lesson that we learned from here and then apply it to the RC circuit differential equation, because they're the same format. So then what will that be? Y of x will be equal to, we didn't solve for a yet, so a is just a, but then we say b has to be negative 1 over 6x, right, plus d has to be 18. And then now what does a have to be? How do we know what a has to be? Well, every differential equation will also have an initial condition or final condition, some condition that the y satisfies. You might be told something like y of 0 is 0. That means when the x is 0, y starts at 0. So the y function starts at the origin. Or you might be given some other condition. It doesn't necessarily have to be initial condition. It could be anything, some condition. So then if you're given this, then you can put it into here, and then so that will help you to solve for the a. So you say y of 0 is equal to a e to the 0, right? E to the 0 plus 18. And then you're told that that's equal to 0, right? In this case, y of 0 is 0. So then y of 0 is a to the 0 plus 18. And then this is 1. And then so a must be negative 18. So therefore, to solve for the a, you do y of x equals negative 18 e to the minus 1 over 6x plus 18. Right, so this is here negative 18, but that's only if the initial condition was 0. If x 0, y was 0. If something else, then you could put that value here, you see. Okay, so now how do we apply what we learned from here to there? So we could say, in our case, the q is the y, right? You have y prime, so you have here q prime. So the q, and then is its function of time. And then so it's going to be a e to the bt plus d. So it's a function of time, not x, right? And then you have here a to the bt plus d. And now what can we conclude about the d? What did we get here? 18. So the d was 6 times 3, right? 6 times 3. And then how did we get that? 6 times 3. So literally it's whatever value is here. So this number must be whatever value is here times whatever value is there. You see? So that's how we can apply the generality there. This times this, so this times that. So it's C times VB. CVB. Right? And then the B was what? The B was negative 2 times 3. So then this times this, right? This times this. So then it's this times this. So this times this. But then negative, so essentially if this whatever here, you're multiplying it by there, and then you're putting it as a negative 1 over TRC. See what I did? So it's 2 goes there because it's 6. So then you just have here negative this times this on the bottom. And then that's negative 1 over 6. Now the A will depend on the initial condition. So let's just take our default circuit will be a capacitor that is uncharged. Although I could show you what would happen if it was charged initially, right? So so let's see here. So then if it is uncharged, what do? We say Q as a 0 is A e to the 0 plus CVB, and that's equal to 0. So I do the same thing that I did down here. Then I got A is negative 18. So here it's going to come out that the A is negative of this. Same thing. So A is negative CVB, and then we put that into there. So Q as a function of T. So I'll say this is the general solution with any initial condition, but then I'll also show you this is general with any initial condition. General with any initial condition. Then I'll do the initial condition. So I'll apply the initial condition, and then I'll get A is negative CVB. I'll factor out the CVB. Okay. Yeah, cool.